we're going to expand what we know about some characteristics of function, maybe add some new vocabulary while reviewing some things that you know already. So we're going to talk about ways to describe things like the roller coaster in terms of how fast you might be going as you're heading down or heading up a specific part of the roller coaster. When were you at the maximum height on the coaster and that sort of thing. So the terms that we'll be introducing or reviewing today are increasing, decreasing, concave up and down, continuity, and maximum minimum values of a function. Okay, so some of these terms will probably be familiar to you, others may be new. We're going to define them very informally. We'll need calculus for a formal definition, but understanding what they look like, how to describe the behavior will help us then later on when we layer the calculus and the algebra on top of it to actually be able to define the terms and to find where this behavior is occurring. So we're going to just draw pictures and talk in general, and then we'll add calculus in the next chapter and we'll be able to describe these terms more specifically. So a function is increasing, and I expect you've seen this in your pre-calculus course. A function is increasing if it looks like this in general. So one way to think about a function increasing is that it's as x increases, y increases. We could also say that the function is rising to the right. But really, calculus is more concerned with describing the behavior, that behavior in terms of slopes. Calculus is a lot about slopes. So if I were thinking about the slopes, the slope of that graph overall, or the kind of tiny, if I were just to kind of chop it up into little bitty bits, the slope of each little tiny bit would be positive. So in general, the slope of the graph is positive if a graph is increasing. If a graph is decreasing, as you might expect, just the opposite happens. So that graph is something like that. And in this case, as x increases, y decreases would be one way to think about that. We could think about it graphically, that the graph is falling to the right. Or we could think about it in calculus terms in terms of slope, and that graph, mine's a little bumpy there, but that graph, if I were to cut it into tiny little pieces, the slope of each piece, or the overall slope, if I were to join the two ends of that graph, the overall slope is negative. Now we're going to talk about concavity and introduce a couple of different terms related to concavity. You may or may not have talked about this in your pre-calculus course. So a graph is concave up if it looks like this. So let's think about how we would describe that behavior. The graph is both decreasing and increasing, so I can't use those terms specifically because I have both types of behavior. But I can use a description about the slope of the graph. If I think about walking along the graph and kind of the slope at which I would be walking. So on the decreasing part of the graph, this portion of the graph, I have a negative slope throughout that entire portion of the graph, but I have a steeper negative slope at the beginning than I do at the kind of the bottom of that curve. So my slopes on this side of the graph are negative, but they're getting bigger. They're negative, but getting less negative, or moving towards zero. If I think about the increasing portion of the graph, then my slope here starts near zero. By the time I get to this portion of the graph, I have a much steeper positive slope. So my slopes on the increasing portion of the graph are also increasing. So over the entire concave up portion of the graph, I have slopes that are getting that are increasing. So I'm either decreasing at a decreasing rate or increasing at an increasing rate. In general, my slopes are increasing if I'm concave up, meaning getting less negative if my slopes are negative, or more positive if my slopes are positive. Graphically, I might describe that concave up behavior as a graph that holds water, or that's cup-shaped or kind of smiley face shaped. And it doesn't have to be a full-on smiley face. It can be a little more subtle, kind of like that. This little portion of the graph there is concave up, even though it's not a really happy smiley face. Concave down, as you might expect, is the opposite behavior. So it looks like a frowny face or an umbrella. It would dump water. And notice that this little concave, where that concave down graph, I do have increasing and decreasing behavior. But if I look at my increasing behavior, my slopes start out really positive, a large positive slope there, and then as I'm kind of walking along the graph, I'm slowing down. So my slopes are getting closer and closer to zero. The slope right here might even be zero. And so I have positive slopes that are getting smaller. On the decreasing portion of the graph, my slopes get more and more negative. So I'm kind of speeding up there, getting more and more negative. So I'm concave down if the slopes are decreasing. So they're getting more negative, steeper negative, or less positive, closer to zero on the positive side. This graph is going to dump water or be a frowny face. A graph is continuous. Almost all the graphs we've looked at so far have been continuous, and you really hope your roller coaster is continuous. A graph is continuous if there are no breaks in it. Or, some of you may have learned this definition before, you can draw it without lifting your pencil. An inflection point is where concavity changes. So let's draw a picture of that. So let's say I was riding on the roller coaster, so I bottom out, and then I head towards the top of the next hill. I know that I'm concave up right through here. I'm concave down by the time I get to the top of the hill. That's very concave down. This is very smiley. This is very frowny. So the switchover occurs kind of right in here. That would be an inflection point. An inflection point is the steepest portion of the graph. That's where the slopes are changing behavior. So it's always the steepest portion of the graph, and it's where the graph is changing from concave up to concave down, or I could have a change from concave down to concave up, and that would occur somewhere right in here. And that one. Let's talk about local maximums and minimums. I know that you've talked about these in previous courses, so let's just remind ourselves of the formal definition of those. So a local maximum is this point. It's the very top point. The maximum is a y value, because we judge top based on y, not on x. So a local maximum is the largest y value in the near neighborhood. For a graph. How's that for a very formal definition? We will get a better definition once we know some calculus of local maximums. Local minimum, it's just the opposite. It's the smallest y value. And notice again that maximums and minimums are y values, not ordered pairs, not x values. Everything else, when we talk about graph behavior, we do it in terms of x, in terms of the independent variable, except for maxes and mins. And we talk about maxes and mins in terms of y, the largest and smallest y value. Okay, let's apply this, just making sure that we can answer questions correctly, write the notation correctly, and that sort of thing. So here's a whole set of questions about the terms we just talked about. I'm going to go through these rather quickly. I'm more concerned about your understanding the notation from here, and then we'll practice in class. But it's good. I think it's good for you to have seen an example. So we're going to start with roots. Remember, roots on a graph are x-intercepts. That's another name for roots. I have 3 x-intercepts, one here, one here, one here. Again, I'm going with what appears to be true, and it appears that the x-intercepts are -2, 0, and 3. Notice the notation there. I wrote x equals. I didn't just write 3 points hanging out there in space. The y values for each of those is 0, which has to be true if I'm finding a root or an x-intercept, so I only need to list x's. If I'm asked where a graph is positive, I'm looking for y values above the x-axis, so positive y values. So for this graph, if we were talking about positive behavior, we would be talking about this section of the graph. If I'm talking about sections of graphs, I'm talking about intervals. I always list those in terms of x, and I always write them as smallest x to largest x. Notice the open brackets there, because at -2 and at 0, the y value is 0, so the graph is neither positive nor negative at those x-intercepts or roots. Oh, there's another place where the graph is positive out here on the end. So I'm going to list that as well, and again, interval notation, smallest x, comma, largest x. Left x, right x. If I'm asked for where the graph is negative, then I'm looking for values below the x-axis, and that happens from x is 0 to x is 3. So interval notation, x is 0 to x is 3, and that's the only place I have negative values. If I'm looking for where the function is increasing, remember that's when the function is rising to the right or going uphill. Slopes are positive, so this graph has positive slope here, and again here. So that graph is increasing from x is -2 up to, it looks like -1. And again, we're just going on appearances at this point, getting used to the terminology and how it corresponds to the graph. And then the graph is increasing again. Oh, do the whole thing all the way through here, positive slope. So maybe 1.5 or so up to 4. If I'm looking for where the graph is decreasing, that's going to be where it's going downhill or falling to the right, or the slopes are negative. This graph has negative slopes through here. So from -1, x is -1, up to x is 1.5. I'll bet 1.5 before. You do have some flexibility. I can't tell exactly where that graph, if that's 1.5 or 1 3/4 or 1.75, I don't know. And so you have some flexibility there in terms of interpreting that graph, because we're just doing it visually. As for a local maximum and minimum, I remember that maxes and mins are y values. So I have a local maximum here, a local minimum here. I have a maximum here, but the graph cuts off, so I'm not really sure if that's the largest y value or if it continues to be positive. And so I'm just going to list these two. So I have a local maximum of, it looks like 1, 2, 3, 4, 5, maybe 5. 1, 2, 3, 4, maybe 4. So local maximum of 4, that's my y value. And then if I want to list x, I can, at x is -1. But I don't have to. So if I just say local maximum 4, that's it. It's the y value when I talk about local maxes and mins. And then I have a local minimum at, I think that's -9. So of -9 at x equals 5. Then I'm My next set of questions is about concavity. I'm asked where the graph is concave up. I remember that means where the graph looks like a smiley face. So this portion of the graph, it's where my slopes are increasing, so getting less negative through this portion of the graph, or more positive as through this portion of the graph. This would be an inflection point. I'm not asked for that, but that's where I've got that switch over where I can actually see the smiley start to begin. So my concave up portion of the graph is from 0 to 4, so as much as I can see anyway. My graph is concave down where I've got a frowny face, or where my slopes are decreasing, positive but getting smaller, negative or getting bigger. So decreasing if I listed them in order. So that appears to be from -2 up to 0. This point, the point 0, 0, is an inflection point because that's where I switch over being concave down to being concave up. I know I'm very, very concave up right through here, very, very concave down right through there. The switch over has to occur somewhere in between. Thinking about continuity, I'm just going to label these graphs and you can see whether or not you agree. This graph is not continuous over its entire graph. This graph is not continuous over its entire graph. This one is. This one's not. This one is. This one is. So if I could draw the entire graph pictured without lifting my pencil, it's continuous. If I can't, it is not continuous.